Everyone talks about hydrogen. Governments announce gigawatts of electrolyzer capacity. Companies compete over stack efficiency. Investors debate whether $2 per kilogram is realistic. Entire national strategies are built around the molecule. But beneath all of that ambition sits something quieter, something less visible but arguably more decisive. Silicon carbide. If hydrogen is the molecule of the energy transition, silicon carbide is the material quietly controlling the electrons that make the transition possible. And without those electrons being controlled precisely, efficiently, and at scale, hydrogen does not work. Solar does not scale. EV charging slows down. Data centers overheat grids. The entire electrification story begins to strain. The uncomfortable possibility is this. The energy transition may be less constrained by hydrogen production than by semiconductor physics. To understand why, we need to step back from molecules and focus on electrons. Every clean energy technology, solar panels, wind turbines, batteries, EV drivetrains, electrolyzers, depends on power conversion. Solar panels generate DC electricity. Grids operate on AC. Batteries store DC but deliver AC. Electrolyzers require tightly regulated DC derived from AC. Electric vehicles convert DC battery power into AC for motors. Between all these transitions sit power electronic devices. They switch current on and off at high frequency. They regulate voltage. They convert AC to DC and DC to AC. They manage heat, harmonics, and grid stability. And at the heart of these power electronic systems are semiconductor switches. For decades, most of these switches were made from silicon. Silicon IGBTs dominated industrial inverters and converters. They were reliable and relatively inexpensive. But as the energy transition pushes toward higher voltages, higher switching frequencies, and greater efficiency, silicon is reaching physical limits. That is where silicon carbide enters. Silicon carbide is a wide-bandgap semiconductor. Compared to traditional silicon, it can operate at higher voltages, higher temperatures, and higher switching speeds with lower losses. In practical terms, that means more efficient power conversion, smaller cooling systems, lighter equipment, and greater overall system performance. Now consider hydrogen. Electrolyzers are fundamentally DC devices. They require precisely controlled current to split water efficiently. The electricity feeding them typically arrives as AC from the grid or renewable assets. Converting that AC into stable DC requires rectifiers and switching modules. Losses in that conversion process directly increase the cost of hydrogen. If your conversion system loses even 2% more energy than expected, and you operate at hundreds of megawatts, that inefficiency compounds over thousands of hours per year. It raises operating cost. It raises the levelized cost of hydrogen. It reduces competitive edge. Silicon carbide devices reduce switching losses and conduction losses in these systems. That means more of the renewable electricity actually becomes hydrogen rather than heat. This is not marginal. At scale, a 1 to 2% efficiency improvement can determine whether a project hits cost targets or misses them. When developers chase $2 per kilogram, incremental efficiency matters. But hydrogen is only one piece. Electric vehicles rely on inverters to convert DC battery power into AC for motors. Faster switching allows higher efficiency and smaller components. That means lighter vehicles and longer range. Fast chargers require high-voltage converters capable of handling extreme power levels. Silicon carbide improves efficiency and reduces cooling requirements in these stations. Solar farms depend on inverters to synchronize DC panel output with grid AC frequency. As renewable penetration rises, grid stability becomes more complex. Inverters must respond quickly to frequency fluctuations and voltage disturbances. Higher switching speeds enable better control algorithms. Data centers, driven by artificial intelligence workloads, demand enormous amounts of stable power. Their power supplies and backup systems rely on advanced converters. As AI accelerates electricity demand growth, the stress on power electronics increases. In other words, the energy transition is not just about producing clean electricity or clean molecules. It is about converting and conditioning electricity efficiently at every stage. If silicon carbide enables higher efficiency conversion across solar, EVs, batteries, and hydrogen, its impact spans the entire energy ecosystem. This brings us to system stress. As electricity demand grows and renewable penetration increases, grids face instability challenges. more nonlinear loads, more variable generation, more harmonics, more rapid ramping requirements. Hydrogen is often presented as a solution to intermittency. When there is excess wind or solar, electrolysis can absorb it. But this flexibility depends entirely on power electronics that can ramp safely and quickly without degrading equipment. The switching devices must handle dynamic conditions. If silicon carbide improves dynamic performance and reduces thermal stress, it enhances that flexibility narrative. Now consider survivability under hostile economics. If subsidies decline, if capital tightens, if utilization rates fall below optimistic projections, which projects survive? Those with higher efficiency and lower operational losses have better margins. Those with better electrical architecture can monetize grid services. Those with lower thermal stress may have longer equipment life and reduced maintenance cost. Silicon carbide influences all of these. This is the competitive edge lens. Under system stress, marginal efficiency improvements are not optional luxuries. They are survival mechanisms. But there is another layer, supply chain geopolitics. Silicon carbide wafer production is concentrated among a limited number of manufacturers globally. Scaling wide-bandgap semiconductor production requires specialized crystal growth techniques and manufacturing facilities. If the energy transition accelerates faster than silicon carbide supply expands, bottlenecks could emerge. This would not show up in hydrogen headlines. It would appear as longer lead times for inverters and converters. Projects would be delayed not because electrolyzers are unavailable, but because switching modules are. That possibility reframes strategic risk. Governments discuss hydrogen independence and energy sovereignty, but semiconductor dependence may be the more immediate constraint. If wide-bandgap devices are critical for efficient electrification, controlling their supply chain becomes strategically important. The narrative shifts from molecules to materials. Let's connect this to cost per kilogram. The levelized cost of hydrogen depends heavily on electricity cost and system efficiency. Electricity often represents the majority of operating cost. If conversion losses are higher, more electricity is needed to produce the same hydrogen output. If switching efficiency improves, electricity consumption drops. Even a small reduction in losses can translate into measurable cost savings across gigawatt-scale operations. Furthermore, higher switching frequencies allow smaller passive components, smaller inductors, capacitors, and transformers. That can reduce capital expenditure and footprint. For industrial hubs where land and integration space are constrained, footprint matters. Footprint influences permitting timelines. Permitting influences time to deploy. Time to deploy influences cost of capital. Again, a semiconductor material influences finance. This is why the energy transition cannot be understood purely through the lens of hydrogen capacity announcements. It is a layered system. Electrons must be generated, they must be converted, they must be stabilized. Only then can they split water into hydrogen. If we misdiagnose the constraint, we misallocate capital. Now consider artificial intelligence. AI-driven data centers are increasing global power demand and straining grids. This forces utilities to invest in transmission, storage, and flexible loads. Hydrogen plants may compete with data centers for grid access. Both depend on high-efficiency conversion systems. If silicon carbide devices enable more compact, efficient infrastructure, they indirectly expand the feasible deployment envelope for both sectors. The energy transition is becoming an electronics transition. Solar panels are semiconductor devices. Batteries depend on electronic management systems. EV drivetrains rely on inverter modules. Hydrogen production depends on rectifiers. Grid stability depends on fast-switching converters. The deeper we go, the more we see that clean energy is an applied semiconductor story. This does not mean hydrogen is irrelevant. It means hydrogen is downstream of electron control. If silicon carbide technology stagnates or supply tightens, efficiency gains slow. If efficiency gains slow, cost reductions stall. If cost reductions stall, project pipelines shrink. That is why this material might matter more than hydrogen itself. Hydrogen strategies often revolve around resource geography. Where wind is strong, where solar is abundant, where water is available. But semiconductor strategy revolves around fabrication capability and material science. These two worlds are converging. Industrial hubs planning hydrogen clusters should be evaluating not only electrolyzer suppliers but also power electronics architecture. Which switching devices are used? What are the expected losses? What are the thermal margins? How resilient is the supply chain? These are not peripheral questions. They influence long-term viability. For developers and investors navigating these layers, structured system-level understanding becomes critical. H2 Hub by Renee Energy exists precisely to explore these real-world integration and cost dynamics, where materials, electrons, capital, and infrastructure collide. As we move deeper into this decade, the energy conversation will mature. The easy narrative, build more renewables, produce more hydrogen, will give way to a harder one. Manage conversion, control stability, secure materials, survive system stress. Silicon carbide may never appear on political podiums. It will not headline climate conferences. But inside inverter cabinets and rectifier stacks, it will determine efficiency, reliability, and scalability. Hydrogen may carry the molecule banner, but the electrons do the work, and the electrons are governed by switching physics. The next energy era will not be won solely by those who control molecules. It will be shaped by those who master materials that discipline electrons. That is why silicon carbide might matter more than hydrogen.